Welcome to the third video in this series of logarithmic and exponential functions. This one is about solving equations. Before we can get to the business of solving equations, we have to talk about converting between logarithmic and exponential form. Here's what I mean by that. Suppose we have an equation like this. This is an equation that has a logarithm in it. Because it's in a specific form, logarithm on one side, isolated, and non-logarithm on the other, we can convert that by simply moving things around into a different order, into an exponential form. We're not solving a math problem here. I'm simply talking about converting an equation from one format to another. We can also convert in the reverse order. Suppose we had a statement such as this one, which is an exponential equation. We could convert that back into a logarithmic equation by just taking the 2, 3, and the 8 and rearranging the order in the appropriate way, and now we have a logarithmic statement. Now this may seem a little strange, so let's go into a quick diversion and we'll come right back to this. This is an obvious statement in mathematics. I can move the order of the terms around and turn it into a subtraction statement. There's other ways to do this, of course, but I bring this up because what we just saw a minute ago with logarithms and exponentials is that we're not solving a math problem. We're just changing one statement into a new format, much like we change an addition statement into a subtraction statement from what you see on your screen now. With the perspective that we're not solving math problems, we're simply starting by the changing of a format of an equation, let's look at the same ones again. When I say these two equations are equivalent, I mean that either one of them could be converted into the other. If one of them is true, then so is the other. When I said these two equations are equivalent, it's because both of them are true statements, one logarithmic and one exponential, using the same numbers. So we're going to use the idea of converting to actually solve equations that involve logarithmic and exponential functions. Let's take a look at how we can use this notion of converting to solve exponential equations. Here's an exponential equation. By the way, it's worth noting that an exponential equation doesn't mean an equation with an exponent. We typically mean an equation with a variable in the exponent, which is a little different, but we do have a variable in the exponent here, so let's go about the business of solving this. Well, if we want to solve for x, and the x is inside the exponent, how are we going to do some algebra to get that x to a point where we can solve for it? Well, one of the best ways to do that is to convert. But this is the conversion formula that we saw on the last screen. If you look at the purple in the center of your screen, the yb and the x there can be any algebraic expressions or numbers, and this is just a way to rearrange them. So what I've done is I've rearranged those here. You may not see it right away, and if you need to pause the video, do that. But I recommend before continuing that you pause and convince yourself that I have rearranged these expressions in a logical way and converted an exponential equation into a logarithmic one. Well, why is that beneficial? The equation doesn't look any simpler now than it did before. But see now, the variable x is no longer inside of the exponent. And that makes it easier to solve now. So all I have to do now to get x by itself is to add 2 to both sides. That will cancel out the minus 2, as you can see here. Now what I've got on the right side of the equation is a number plus a logarithm. I'll worry about simplifying that later if I even can. And now to solve for x, I should obviously divide both sides by 4. And I've now isolated the x and numerically solved for x. Now there is some simplification that can be done here, but I want to put that thought on hold and just stop where we've isolated x and essentially solve for an expression that will ultimately lead to a simplified version of that answer. Pausing the problem midway through, I want to stop and look at a very similar problem. Compare these two problems side by side. They're almost identical, as you can see. One doesn't look much different than the other, so you can imagine if you were solving this one, you would do exactly the same steps. Fair enough. Nothing's really changed. But fundamentally, these two answers are going to end up looking very different. They may not look very different to you now, but there's something you may not have considered yet. Let's go down that road. Each one of these answers has a logarithm in it. If either one of these logarithms were simplifiable, then we would be obligated by the traditions of math to continue to simplify the answer. Well, it turns out one of these two logarithms is simplifiable and one of them isn't. Well, how would you know? Well, it just so happens, for the one on the left, that the base and the argument, 9 and 243, are both powers of 3. You might ask yourself, well, I, as a student in a mathematics course, would never recognize that. 243 may not sound like a special number to you in particular. And the idea here is this. I don't expect that my students would necessarily have every number that's a power of 3 memorized. Did you know that 3 to the 5th was 243? Most people don't have that memorized. But here's the thought. When you're simplifying a logarithm, you need to be on the lookout for your base and argument being both powers of 3 or something, because if that's the case, there's going to be a simplifiability there. Watch as I simplify log base 9 of 243, using the fact that they have that 9 and 243 are both powers of 3. To simplify this logarithm is the same as to solve for x in this equation. I'm sorry, to solve for y in this equation. And so, to solve for y in this equation, I'm simply going to express 9 as 3 squared and 243 as 3 to the 5th. Using a special rule for algebra for exponents raised to exponents, I can now drop the 3's. After all, if 3 to one power equals 3 to another power, those powers must be equal. And I can now solve for x by dividing by 2. Sorry, solve for y. And now that I remember that y isn't really an issue in this problem, y is something that we made up to solve or simplify this logarithm. And so now I know that log base 9 of 243 is 5 halves. And now I can continue to solve this equation for x just using basic arithmetic. I can do 2 plus 5 halves in my numerator. It won't show the fraction work here, but it does work out to 9 halves. And again, I won't show the fraction details. If you're not comfortable with fractions, you may want to pause and examine all this. But 9 halves divided by 4 does eventually turn out to be 9/8, and I've now solved for x in the first equation. And the reason I was able to simplify the answer beyond the logarithmic form is because log base 9 of 243 turned out to be simplifiable. By contrast, log base 8 of 243 isn't simplifiable. 8 and 243 are not both powers of the same number. 8 is a power of 2, 243 is a power of 3, but there's no what they call common base here. And so there isn't anything that I can do to simplify this logarithm here. Now, if I wanted to, I could use a calculator to get a decimal approximation for that logarithm. I could then use that decimal approximation to continue to simplify the problem and get a decimal approximation answer for x. And while there's nothing wrong with that, that's not the typical thing to do in most algebra classes. In most algebra classes, we don't use calculators. And therefore, none of that work is, well, correct, is particularly relevant here. And so what we see in this case is that two problems that look almost identical have very different looking answers because of the numbers that were in them. And so always be on the lookout in logarithmic and exponential situations for whether two numbers are a power of the same thing. The fact that 9 and 243 were both powers of 3 was critical for our ability to simplify the problem on the left. Let's take a look at another exponential equation. By that I mean we have an exponent and there's a variable in that exponent. Well, in order to solve for x, we're going to have to treat this a little differently than the two we saw in the previous example. Notice the two on the middle right side of your screen have the exponential function on one side and the number, the 243, on the other. And in the previous example, we were then able to convert these to logarithmic form and ultimately solve for x. Here's the issue. This equation we're trying to solve now is not in the format that allows it to be converted. In other words, the exponential function is not isolated yet. So, unlike the last problems, I've got some work to do here before I can convert. Here's the work that I have to do. I have to do something called isolate the exponential function. When I say exponential function, I mean the base and the exponent together, the entire 9 to the x minus 4 that you see in red here. I've got to isolate that. Before I do, I want you to think about something. I'm going to put an R here for red. Other than that, these are the same equation. If you were trying to solve this equation for R, which is the same as this equation, it wouldn't be hard to convince you that you needed to subtract 1 and then divide by 3 to isolate the R. We're not going to actually do that here, but I think that's pretty clear. If you've reached this level, that seems basic to you. So in the same vein, I need to isolate the exponential function here by subtracting 1 and then dividing by 3. Watch as I do that. Here I'm subtracting 1 from both sides. Here I'm dividing both sides by 3. And now what I've done is I've isolated my exponential function. Notice what's in red, the 9 to the x minus 4. I haven't messed with that yet. I've simply done the basic algebra necessary to get that exponential function isolated, or by itself. Now that I've done that, now I can convert to logarithmic form by simply moving the base 9 from one side to the log base 9 on the other. And that's your basic conversion principle. Well, the beauty of converting is the variable x is no longer in the exponent. That's why we convert. And now, to solve for x, I simply need to add 4 to both sides. And I've now isolated x. The only question left is in simplifiability. In other words, is there anything about log base 9 of 5 that I can simplify? Not really. 9 is a power of 3 and 5 is a power of 5. There's no common base there for me to simplify log base 9 of 5, so short of using a calculator, which we don't normally do in algebra courses, that is as simplified as the answer could get, and that is the final answer in logarithmic form. Let's take a look at one more problem that involves us solving an exponential equation. So, in order to solve this equation for x, the first thing that's worth noting is that the x is inside of an exponent of an exponential function. The only fundamental difference between this problem and the last one is on the last problem, we had a whole number base in our exponential function. I believe it was 9. And in this problem, we have e. Remember, e is not a variable. E is the number 2.718 approximately, and it's a special number in mathematics, but we need to be thinking of e as a number here. Okay, so I have an x in the exponent of an exponential function, and therefore I have to isolate that exponential function in order to solve for x. Now it's worth noting here that this problem is not saying that we're raising 3e to some power. We're multiplying 3 by e raised to a power. Restated, my exponential function does not involve the 3 itself. So now what I want to do is isolate what you may see in red here as e to the 2x minus 1. Well, in order to isolate that, it makes sense to subtract 4 from both sides. But there's still a 3 in front of my exponential function, so I haven't isolated it yet. And to isolate that now, I'll have to divide both sides by 3. Now I haven't solved for x yet, but what I have done is gotten the exponential function isolated. It is now by itself on one side of the equation. I still have an x, and that x is still in the exponent. So in order to get rid of the fact that the x is in the exponent, we should convert to logarithmic form. So the e as the base of the exponential function on the left side essentially disappears and reemerges as a logarithm base e on the other side. That's the basic principle of conversion. Now, you're completely free to leave log base e written that way. Remember, e is 2.718 approximately. There's no way to simplify log base e of 7 without a calculator, and so you're welcome to leave it in that format. You may recall, however, that there's a tradition that instead of writing log base e, we write ln, which represents logarithm natural, also known as the natural logarithm. You're not required whatsoever to write ln, but it's a tradition that I'm going to stick to because I don't like writing log base e. To me, that looks strange. Okay, now, remember I'm trying to solve for x, but look what's happened now. The x is no longer in the exponent. So now to solve for x, wouldn't I just have to add 1 to both sides and then divide by 2? So that's what I'll do. I'll add 1 to both sides. Now 1 plus the natural log of 7 doesn't become the natural log of 8 or anything like that. Be careful. A whole number added to a logarithm doesn't generally simplify. Not without a calculator. And now to solve for x, I'll divide both sides by 2. And I now have x isolated. As far as simplifiability goes, is this simplifiable? Not really, because the natural log of 7 can't be simplified without a calculator. Therefore, there's not really anything else I can do. So in most algebra classes, we leave this as the answer for x, as opposed to turning it into decimal format, which we could do if we were so inclined. All right, now we're going to shift gears to logarithmic equations. You'll notice in the last 3 examples, we were given problems with exponential functions, and we converted them into logarithmic functions for the purpose of answering. But now we're going to look at equations that require the reverse. We're going to look at equations not that end up with logarithms in their answers, but equations that have logarithms in the original problem, such as this one. So here's an equation, and we're trying to solve for x. Well, to solve for x, we've got to get the x by itself. But right now, it's inside the argument of a logarithm. And the only way to sort of free that, as it were, is to get rid of the logarithm. Well, the only way to get rid of a logarithm is to convert this equation to exponential form. And so, in order to do that, I'm going to get rid of the logarithm as shown there. Now, you'll remember that there are equations that guide the conversion between logarithmic and exponential form that you can see here. And those are correct equations. Well, let me share a mental trick with you that I use. I simply move the logarithm away from one side of the equation and have it reappear on the other side as the base of the exponential function. It's equivalent to the formulas you see in purple on the right of your screen. It's just a nice little mental trick so that I don't have to memorize those formulas. Either which way, this is now, after our conversion, become a very simple equation to solve because 3 squared is 9. And now we can use the very basic tools of algebra to isolate and solve for x, which I won't explain because they're pretty simple. Okay, that's our first problem, x equals 5/2. Let's look at another logarithmic equation by comparing it to the one we did on the last one. And the one on the right is the problem that we just finished. What makes these problems different is that on the problem in the right, the logarithm is isolated, whereas in the problem in the left, the logarithm is buried inside of some other algebraic expressions and is not isolated. So unlike the last problem, where we immediately converted out of logarithmic form into exponential, here we're going to have to isolate the logarithm first before we can convert and get rid of the logarithm. So in order to isolate the logarithm, we'll do all of the basic algebra that one would normally do. First, let's add 7 to both sides. This will cancel out the minus 7. And then, because the logarithm still isn't isolated, let's divide both sides by 3 to isolate the logarithm. Now you'll notice that the logarithm has been algebraically isolated, and now that it has, we're ready to convert to exponential form. So converting this to exponential form will get rid of the logarithm on one side and turn it into an exponential function on the other. Again, you'll notice the log base 8 disappeared from one side and turned into the base of an exponential function on the other side. In essence, the 2/3 will bump up, so to speak, as an exponent. Now that we've converted to exponential form, we've isolated the x. We now have a solution. X equals 8 raised to the 2/3 power. And while I sometimes might stop here and say I've solved for x, in this particular case, that simplifies to 4. That's not something most people can see right off the top of their head, so let me explain. 8 to the 2/3 power, you'll recall, means the cube root of 8 squared. That's the definition of a fraction exponent. Well, the reason why this is simplifiable is because the cube root of 8 is simplifiable. The cube root of 8 is 2. And of course, 2 raised to the 2nd power is 4, which is how I was able to simplify this expression to 4. So while I'm done with the problem, I think it deserves a slightly deeper look here into a similar situation. Done with the problem, the answer is 4. But let's consider a different situation. What if, instead of these numbers having originally been 8, what if they had been 9s? Well, I would have done the same kind of algebra, and instead of 8 to the 2/3, I would have got 9 to the 2/3. There's a fundamental difference between these two problems. Whereas 8 to the 2/3 simplified to 4, 9 to the 2/3 doesn't particularly simplify to anything. I could certainly type it in a calculator. If I did type it in a calculator, I would get about 4.3267, which wouldn't be wrong, but since we typically don't like to use calculators in algebraic environments, I would just leave the answer as 9 to the 2/3. And as similar as these problems are, it's worth noting how fundamentally different the answers look, because in one case, 8 to the 2/3 was simplifiable, but in the other case, 9 to the 2/3 would not be. All right, let's take a look at another example. Here's another logarithmic equation. It's a natural log instead of any other logarithm, but a logarithmic equation nonetheless. And the first thing that we have to do, of course, is isolate the logarithm so that we can get rid of the logarithm. Well, to isolate the logarithm, we'll do our basic algebra. Subtract 2 from both sides in this case. But notice that doesn't completely isolate the logarithm. It still has a negative in front of it. That negative natural log of x means -1 times the natural log of x. So I'm going to multiply both sides by -1, or you could think of it as dividing both sides by -1. And that essentially brings me to this equation. Now it's worth noting here that this is not some magic trick where the negative sign flies over to the other side. This is actual algebra. I multiplied both sides of this equation by -1. And now that I've isolated the logarithm, it's time to convert to exponential form. But before we do that, remember, the natural logarithm is really just a shorter way of writing log base e. I haven't done any mathematics here. I'm just reminding you what the natural logarithm means. Okay, now to convert this to exponential form, we will essentially get rid of the logarithm base e on one side and turn the other side into an exponential function. Notice the change here. Log base e disappeared, and a base e exponential function appeared on the other side, essentially bumping up the -3 as the argument or exponent of that function. So now I've converted to exponential form, and notice I've gotten rid of the logarithm, and now I'm much freer and easier to solve for x than I would have been. All I have to do to solve for x now is subtract 1 from both sides. And I now have the value of x. I don't personally like equations with the x on the right. I'm going to switch this around, and there's our solution. When we're done with the problem, it's worth noting that you may, from time to time, see this kind of an answer written this way instead. Because recall, e to the -3 means the reciprocal of e to the 3. Either one is fine. There may even be courses in which you convert this entire thing into a decimal, which it could be, of course, because let's not forget that e is 2.718 approximately. So if I wanted to convert this whole thing to a decimal, I could, but that's not my solving style. I tend to like to do these without calculators. Okay, so let's look at our last logarithmic equation in this video. In order to solve for x, as usual, as in the last two problems, we're going to need to isolate the logarithmic function so that we can get rid of the logarithmic function and ultimately solve for x. But here we have two logarithmic functions. So what I'm going to do is I'm going to use the sum rule that allows me to add two logarithms. What I've just done is add these two logarithms. Let me remind you from the last video that when you add logarithms together of like bases, you multiply the arguments together. Now I didn't show my work here, but I basically used the FOIL process to multiply the two arguments together. And that's where I got x squared minus 2x minus 35. If you need to pause the video to check the FOIL yourself to know what's going on, that wouldn't be a bad idea. And we'll move on. So what we've done here is we've now isolated the logarithm, so we can now convert it into exponential form. Remember, we're trying to solve for x here, but with x's trapped inside of the argument of a logarithm, there's no way that we'll algebraically be able to do that. So as soon as I convert to exponential form, I've gotten rid of the logarithm. Remember my mental perspective on this. The logarithm function disappears from one side of the equation and reappears as the base of an exponential function on the other, essentially bumping up the 3 as a power or an argument to that exponential function. So that is the conversion out of logarithmic into exponential form. Well, notice what we have now. We have a basic equation which you've probably learned to solve a long time ago if you've reached this level of mathematics. And so let me remind you how this works. First of all, 4 cubed on the right side of the equation, that's the same as 64. Maybe now this equation looks a little bit more familiar to you. You may recall this is a quadratic equation and needs to be set equal to 0 and solved. I'm not going to give a lot of algebraic detail here because our focus is on logarithms. So you may want to pause the video at this point and try to solve this equation yourself. So go ahead and hit pause, solve this equation, and hit play when you're ready to continue. This should have been something like what you did, or maybe you used the quadratic formula. Either which way, the algebra of the quadratic equation is not the focus of this video, so one way or another, use your prior skills to solve for x equals -9 and x equals 11. Now, it may feel like we're done with this problem because we've solved for x, and you would think so. But there's something that we've never discussed before in my videos called extraneous solutions. Let's go into this for just a moment. You remember at the beginning of this problem when we multiplied those two arguments together to get log base 4 of x squared minus 2x minus 35? We were making an implicit assumption there that the arguments on the top line were positive. Now, earlier in the previous video when we discussed the sum rule, we simply stated that arguments of a logarithm cannot be negative or zero, and we left it at that, and then we would always continue to combine logarithms by multiplying their arguments whenever it was addition. But while we weren't focused on the positive or negative sign of the arguments at the time, it is true that this combining of logarithms is only a valid operation if the original logarithm arguments are positive themselves. What I'm saying is, when we did this very first step of the problem that you see at the top of the screen, we were implicitly assuming that the second and first arguments of the logarithms were positive numbers. Well, it raises an interesting question. Is negative 5 minus x a positive number? Well, it may or may not be, depending on the value of x. Is 7 minus x a positive number? It may or may not be, depending on the value of x. And so what we want to do now is take these implicit assumptions, or restated, the fact that logarithm arguments must be positive, and we want to juxtapose those with these two supposed solutions to this equation. So first I'm going to plug negative 9 into my first assumption, and negative 9 into my second assumption. We're going to plug 11 into our first assumption and into our second assumption, and we're going to analyze these statements for truth. So what we should do now is work out these numbers, and I'm going to work out each one of these. I recommend that before I do, that you pause the video and work out these four expressions. You may see them in purple, and hit play when you're ready to continue. What these expressions work out to leads to interesting analysis. We have four statements here, but two of these statements aren't true. And if those statements aren't true and they were based on the concept of x being 11, then it must not be true that x can be 11 in this equation. And therefore, x equals negative 9 is the only solution to this original equation. By the way, a couple things of note here. Positive 11 would be a solution to the second line that you see at the top of your screen, the one with x squared minus 2x minus 35, but that isn't the equation we're solving. And if all of this discussion on extraneous solutions is a little confusing to you, and it is to very many people, here's a simple fact you can remember to avoid such an extensive analysis. When you get answers to a logarithm equation, the logarithm arguments must always be positive. I'm not saying that answers to logarithm equations have to be positive. That's not the case. Negative 9 is a valid answer here. There's nothing wrong with negative answers. But the reason why 11 turned out not to be a valid solution is because if we were to plug in 11 to the top line or the original equation here, both of those arguments would have been negative. And if either of the arguments is ever negative based on a particular solution, then that solution isn't a solution at all. Okay, the good news is this doesn't happen too often, but it is something that you need to be aware of to check, that arguments are never negative based on an answer that you get to a logarithm equation. And that completes the last problem. And that concludes the third video in this series of 4.